Okay guys, test on Wednesday. Similar format. As usual, nomenclature we did by video. Spectroscopy will be IR. IR only. Any questions about IR? Shelby?
Is there a difference between like a normal carboxylic acid and an anhydride on the...
Anhydride is going to have 2 carbonyl peaks.
Oh, okay. That's it.
Well, anhydride is also not going to have a broad OH.
Okay.
So, I mean, they're easily to distinguish. Questions? Yes?
Is there going to be a multi-step synthesis?
Multi-step synthesis? There won't be any like was on test 2 or like in the workbook, but there may be some variations of that,
So like you give us
like giving line reactions, multiple step line reactions maybe. Okay. In the end, though, the multi-step synthesis really helps you a lot to learn your reactions. Yes?
So in a couple of the mechanisms that we did, like in our American slide, sometimes in the situation of like anhydride, when we have an amine group or something, sometimes we show that like TAE takes the hydrogen directly from the nitrogen, but sometimes we show that HCl takes it and then complexes with, and then TAE complexes with the HCl. So which one do we do? Does it matter? Does that like matter, or I was just confused as to which step we should follow?
It's really either way. You'll see books do it either way. Usually you should use the stronger base whenever you do a base reaction. The stronger base is going to be triethylamine. Triethylamine should take the H. You should never really make HCl.
Okay.
I just showed you how HCl is formed. And then, well, how can we take care of it? We include a base, and then the base can react with HCl. It's all tomatoes and tomatoes. Ultimately, triethylamine is going to end up with the HCl. But I would use triethylamine as soon as you can, as soon as the H becomes acidic. Other questions?
How does combination inhibitors affect like the acidity and basis acidity of like aromatic? When you have like aromatic ring, you have like a NH2 on it. How is the aromaticity of that guy? How basic it is, or how it's
It's just conjugation.
so it's
Talking about being acidic or basic? Well, long parent P orbital is not going to be that basic. Show me an example of what you're talking about, and probably want to compare it to something else. Other questions? Aditi?
And on number 5, on page 43 in the workbook.
I don't have my workbook. Go ahead.
Okay, well, it's a nitrile, like it's like a nitrile attaching methyl reacting with H2S. And in the answer, you show that S acts as the nucleophile and attacks the carbon directly. In that case, would you propionate the nitrogen as would be like under acidic conditions, or would you?
Is the reaction under acidic conditions?
So H2S it's not.
H2S is not a strong acid.
Okay.
Strong acids, there are like 7 of them. You learned them in Gen Chem. HCl, HBr, HI, sulfuric. There's like 6 or 7 strong acids. H2S is not a strong acid. The difference is H2S is a super good nucleophile. Water does not add directly to a nitrile, but H2S will. Sulfur is a very good nucleophile, even in the neutral state. Water would not do that reaction, but H2S will. Other questions? Jordan?
If you're doing an H plus transfer, and like one of the substituents is an anion, do you always transfer the proton to the anion? Because it has like a greater affinity for it.
It's more basic,
So yeah.
as opposed to transferring it where?
Maybe like another group that's ultimately going to be a leaving group. So if you had like an alcohol and like an anion, right? And then
you always, I mean, we learned acid-base chemistry and organic 1, basic. If you got an acidic proton, you're going to be more prone to transferring it to the more basic atom.
Okay.
Also, you can't essentially protonate something under basic conditions. You can't have an acid and a base in the same pot. Like, you can't have a reaction and have hydroxide and H plus and say, okay, at this point in the mechanism, I'm going to use this, and then I'm going to turn around and use this. These don't coexist together. You might learn something like this in Gen Chem, and you do all types of calculations. That's just theoretical calculations. In practice, these don't exist together. Okay? And if you think they're due, you get your money back. And so, the only way you're ever going to show something like this in a mechanism to make that OH a better leaving group is either be under acidic conditions or neutral. You're never going to do this under basic conditions, because this is essentially all you can only get to this by being under acidic conditions. So if you have an OH and you have like an N minus in the same molecule, you're going to transfer the proton here. You would never transfer it here and say, hey, look, I protonated my oxygen. In the meantime, I've got this super basic atom sitting right here. So it just doesn't make acid-base sense.
Okay.
Instead, you'd transfer a proton here, and you'd go neutral. Everything's neutral. Other questions? Yes.
Can you do a proton transfer from something that is neutral to something that is also neutral? For example, like from an OH to like.
Yeah, neutral and neutral,
Okay.
sure.
Alright. That's it.
Because you had neutral and you didn't change your net charge. I mean, you didn't. If you look at it, you didn't change your net charge.
Also, on the page of the chemistry of the nitros, can we do the acidic one, the acidic condition one?
On which one?
The acidic condition one, like in the sheet you gave us, it was pretty clear how to do the basic one. For the acidic, there was like some steps I wasn't really sure about. Can we take time to figure out? It's okay.
What step were you not sure about?
When like the water attacks the carbon and keeps off, not keeps off, but like gives electrons to nitrogen. If that was like, what's like happening? I guess. Does that one step right there?
We could look at it. I pretty much expect you to be able to do that on your own. First step of the mechanism is what?
Taking and nitrogen takes the
Protonate the leader. Protonate the functional group, either carbonyl or nitrile. What's the next step?
Water attacks the carbon and takes off one of the triple bond to the nitrogen.
Yeah. Yeah.
And then H transfer?
If it needs to be done.
Yeah.
Yes.
Other questions? If you want to show it to me, show it to me.
Oh.
After class or anything. Anytime, you can always stop by and show it to me. Right after class. 8:51. Yep, show it to me. Other questions? Yes, last question.
Number 20 in the workbook, for multiple choice, it was like, basically there was one of the groups was a phenol, so it was an oxygen on the benzene, and then it was like a multi-line reaction, and one of the reactions was NaOH and then ETI. And that I think it was an SN2 and it did OET. Is that possible? I thought we couldn't do SN2 on an sp2 carbon.
It's not an sp2 carbon.
So you can still,
You said ethyl what?
FOI, it was just ETI and then it was OH. So
ETI, what is ETI?
ethyl iodide.
Yeah, ethyl iodide. That's not sp2 carbon.
But, oh, so the oxygen, oh, just kidding. Okay, cool, thank you.
What were you kidding about?
Oh, not, I got confused as to where the actual, like, attack was happening, so I was doing it on the,
All right, I understand. Did you draw it all out and look at it?
not that one, no.
See, you didn't draw it out. You're just looking at it, draw everything out, then look at it. Okay? I see that all the time. You guys are just a little bit too quick. Draw it out, do your mechanism, look at it.
Just 50 minutes.
Go ahead.
So you do only just 50 minutes.
Well, if you're going to look at it correctly. All right? For some reason, you were looking at the carbon that the oxygen was on. But that's not the carbon that gets attacked in the reaction. You got it? You got it. Okay. If there's other questions, please stop by anytime. We need to move ahead. Everybody got a handout today? Document camera. Everybody got a handout? No. Was there extras somewhere?
Please.
Okay guys, test 4 is aldehyde ketone chemistry. We did a little aldehyde ketones on the last handout when we were doing some direct additions. Thank you. This is sort of a semi-summary of reactions. An aldehyde or ketone in the box, different reactions we can do. For example, we can make a hydrate, we can make the cyanohydrin, we can make an imine. Most of you, everybody's already made imines in lab. We can refer back to that. There's another handout. I'm going to send it to you by email. I've got it here. It's got some warm-up questions on it. It also includes nomenclature. But this nomenclature is covered on that one nomenclature video, the second half of the video. This is the aldehyde ketone nomenclature for test 4. Most of this handout is miscellaneous things, but very important. Lots of applications of aldehyde ketone chemistry. Lots of applications in biochemistry. You'll also go back to a comprehensive spec problem, and there's some review here. For example, mass spec of aldehydes, ketones. All this you've seen, I've just sort of reviewed it for you. Proton, carbon NMR of aldehydes, ketones. And then there's miscellaneous things that we'll refer to. Please have this printed out for Friday. The purple colored sheet is outlined.
What?
Dr. Stevens,
Yes.
are we going to finish the test tube material?
What did we not finish in the yellow?
Number 9 and on. Rest of the page.
You're right. Let's look at the yellow a little bit. Because we can do these review reactions down here. Number 9, though, Bob, we did, right?
Yeah, we did 9, we didn't do 10.
We didn't do 10. I don't think I'm going to do 10. Let's look at predicted products down here. Product here. Let me just show you products. Answer here would be just tertiary alcohol. How we do? This should be pretty straightforward, guys. That should be just the secondary alcohol, just the methyl. Yeah? I'll come this way with these. That was going to be, it's actually a tertiary alcohol. It's got two ethyl groups, OH.
That would be H plus workup, right?
All these going to require H plus workup. Are they? The last one doesn't. Is that what you?
Yeah.
That's good. It does not require it. But the first three all require H plus workup. That's where the H of the OH comes from. Has to come from workup. Very often you see a reaction like this, it's not going to explicitly say H plus workup. Okay? A lot of times the protonation to go neutral is just not really referred to. These are the neutral products. Down here, that's two additions. You add once, up, down, you get the ethyl ketone, and then you add again, get another ethyl there, O minus picks up, okay? This one down here, I'll draw it here, just going to be the ethyl ketone. Using the Gilman reagent, we're going to recuperate, nice way to make a ketone. Ethyl just adds, replaces the chlorine. This is essentially an ethyl anion, but it's milder. That's an ethyl anion, but its Grignard is stronger. H minus, and that's phenyl minus. These are all pretty much the standard carbonyl chemistry reactions. How do we do on these four? Any questions about these four?
So 10 we just don't need to worry about, or we need to figure it out on our own?
Well, 10 is something that leads us into test 4, and I actually removed it on the handout for test 4. So there's really no use doing it, I don't think. Hydrate is a hindered hydride source. For now, we're not going to be accountable for it. So I removed it from the handout that I just gave you. It only adds once. If you want to know about that reaction, the product of that reaction ultimately with aqueous workup is an aldehyde. There's one other handout that might want to look at something. It wasn't green, it wasn't yellow. Your handout with here it is, it's white. It was covered the outline. Miscellaneous topics. Go ahead.
I know that you don't do S&T on the refrigerator carbon, so we'll say you're not react at all with refrigerator carbon.
You mean the leaving group?
Yeah, yes.
It might do elimination. Cyanide is sufficiently basic, it might do E2. You can show it to me. Okay, in the white handout, near the back, there is a page about some miscellaneous topics. I wanted to move on to allied ketone chemistry, but this is sort of some important information. Carbonic acid, shown here. Okay, carbonic acid is not a stable molecule. If you form carbonic acid, it's immediately going to break down into H2O and CO2. Okay? This is what happens when you take baking soda and add vinegar. What does it do? It bubbles up. One of those bubbles is CO2 coming out of the mixture. Okay? You make your volcano in 3rd grade? Okay. So, that equilibrium will establish, but as the CO2 leaves, the equilibrium adjusts to form more CO2, so it essentially all goes to the right. Okay. Now, while carbonic acid is not stable, first off, is carbonic acid a carboxylic acid derivative?
No, because it's oxidation state.
Carboxylic acid derivatives, the carbon of the carboxylic acid has 3 bonds to a more electronegative atom. All acid derivatives, the carbon has 3 bonds to a more electronegative atom, like a nitrile. 3 bonds to a nitrogen. Does that carbon have 3 bonds to a more electronegative atom?
Yes. 4.
No, it has 4. It's at a different oxidation state. It's not a carboxylic acid derivative. It's at a higher oxidation state. Okay? So this is not a carboxylic acid derivative. But the chemistry of it can be very similar, though. Addition, elimination. You have the O that can leave. Okay? While carbonic acid is not stable, the diesters are stable. This is diethyl carbonate. Diethyl carbonate. The dichloride is stable. That's called commonly phosgene. That's a liquid. Phosgene is actually a gas. Very toxic because it's very electrophilic. Nucleophiles love to attack that carbon. And eventually kick off the chlorines, addition elimination. Okay? Phosgene used to be used as sort of a war gas. Okay? It was actually in one of the James Bond movies where they were in a cave and the bad guys gassed the cave with phosgene. And then Bond or somebody said, "Run, phosgene!" Okay? You don't want to breathe that stuff. All your nucleophiles will react with it. Water will react with it and make HCl. HCl will cause damage. The diamide is stable. Anybody know the name of the diamide? Common name. Come on now, you need to, all you biology majors know this. What is it?
Oh, that's
That's urea, right? Okay, urea. Mixed derivatives are stable. For example, you can have like an amide on one side, ester on the other. That's called ethyl carbamate. Okay? Carbonic acid is not stable, but lots of these without the H are stable. Of course, you can also have, why is that called diethyl carbonate? What if you took the 2 ethyls off and it was minus minus? What is this?
Dichlorate?
Carbonate. It's carbonate.
Oh.
Okay, you put ethyl here and ethyl here, it's diethyl carbonate. Carbonate. Okay, but you can have K plus and K plus. What is this? Potassium carbonate, K2CO3. It's a solid. Okay? These anions are stable, but if you put them in acid, what happens? Each oxygen picks up an H, forms carbonic acid, plus KCl, or whatever your anion is. The carbonic acid immediately breaks down to CO2, and so that's why it will bubble up. Okay?
Will it do that in water? Is it strong enough to be protein?
It won't take an H from water. Okay? Because that's really not that acidic. This is like, not that basic. It won't take an H from water. So you can dissolve carbonate or bicarbonate water, but you can't dissolve it in acid. If you remember when we talked about deprotonating phenols, bicarbonate will deprotonate a carboxylic acid, but it won't deprotonate a phenol. And phenols are more acidic than water. So if it won't deprotonate phenol, it won't deprotonate water. You got one H there, that's stable, that's sodium bicarbonate. You put the other H on, then it's going to decompose into CO2 and water. And that's sodium carbonate, okay? So these are your carbonic acid derivatives. But the chemistry can be very similar. Addition elimination. Back over in the other handout, must be green. No, it must be yellow. Nope. What's our other handout? Yeah, see, I put things on colored paper. That's the problem with white paper. Okay, we won't worry about it. Down below, another topic. We mentioned nylon. Nylon is a condensation polymer from this here. This is an amino acid, but it's not an alpha amino acid. Okay? Alpha, beta, whatever, something over here. Now, we can get the amine to cyclize and you lose water to make the lactam. That's going to require activation of the OH group somehow. Like converting it to an acid chloride. Then the amine will attack and kick off the chlorine. Otherwise, that's an acid and this is a base. Otherwise, that's just going to take the H. And this game over because this is no longer reactive. Now, if this will condense, that's a general term, condense, and you eliminate water, it can condense and make just a lactam. But again, it's going to require some type of activation to do this, or maybe in the body an enzyme. Okay? The general term is condensation, and that would be just the monomer. Okay, and that's inter. Okay? But another way for this to condense is to polymerize. And that is multiple molecules. This condenses onto the carboxylic acid of another molecule, and then the amine of another molecule condenses onto the carboxylic acid. Again, that would require some type of activation to get these two to react to eliminate water.
Is there a nylon 5 or a nylon 7?
I think they are, yeah. Nylon 6, you have 1, 2, 3, 4, 5. It's the number of carbons in the repeating unit. Nylon 6 is the most common nylon. If we can understand the polymerization, everybody got two hands? Okay, you're lucky. Good. Right hand, let's say the right hand is the carboxylic acid, and the left hand is the amine. Okay? to make the monomer just a cyclic, they come together and they eliminate water, right? Again, I'm not talking about mechanism, but it's some type of mechanism to eliminate that water and to condensate. Okay? Now instead, let's do a polymerization. So instead of this carboxylic acid coming together with the amine, we're going to come together with your neighbor. And so your right hand condenses with the acid condenses with the amine of your neighbor. So condense with her, your amine condenses with her acid. Okay? Now you have an amine left, right? Now you condense with his acid. Now you have an amine left. You condense with his acid. Then what do you got left? An acid. You condense with his amine or something. So you get the idea. Instead of an internal, one group condenses with the group from the other molecule. Okay? And then you would get just a repeating unit. But if you do that, we're not going over the chemistry. If you want to do this, polymer chemistry is its own course. There's lots of practical stuff about how do you get this to polymerize versus how do you get it to just do this. Okay? First off, got to be some type of activation. Otherwise, it means it's going to take the H and game over. So that's how you can polymerize that. And that would be a condensation polymer, eliminating water essentially. Okay, where do we see more other condensation polymers? Proteins. All the proteins in your body are condensation polymers coming from amino acids. But those are alpha amino acids, like histidine. And what are some others? Lysine and glutamate or glutamine, whatever you call it. Or what?
Those are other amino acids.
Glutamate and glutamine?
Yeah.
Okay. Serine and lysine and threonine. Okay, methionine. The amine is on the alpha carbon, but these can also do a polymerization. This attacks with the bonds with the carboxylic acid of another. And between every repeating unit has a different R group. So it's not actually a true repeating unit. It's a variable polymer. And depending on the R's, of course, you get different amino acids. But see, basically it's an amide linkage after it's condensed. Different R groups, those are amino acids. Of course, then the amino acid, that would be your sort of primary structure where you see the actual bonds. So then when you get to biochemistry, actually that's not even called primary structure, that's just sort of your basic organic Lewis structure. But then you start showing structures like this where you just show the repeating unit as sort of a circle. But since these can be very large, then you start showing other structures. And this is showing more of the topography of the big, huge molecule. It's kind of a 30,000-foot view. If you narrow down, you get this here. Okay, so amino acids can be polymerized. Proteins, Nylon 6. I thought I just had the other white handout. What's on the cover of the other white handout? Oh, all the boxes? The box? Yeah, I should make more than one copy. That's probably it right there. Acidity. Drug. No. Yeah, on the back of that white handout with the box on it, there's a reaction here of this amine with this is a carbonic acid derivative. Got a chlorine on one side and an OR on the other. Okay? But it still can react. The nitrogen attacks carbonyl, electrons up. Back down, which leaving group you're going to be more likely to kick off, the chlorine or the oxygen?
Chlorine.
Yeah, so you kick off the chlorine, and now instead of the chlorine, you got that nitrogen bonded there. So that's just a good old, of course something took the H. What took the H? So then bicarbonate, they include it as a base to take the H, so the amine doesn't take the H, although that's not that basic. There's some reactions on there. For example, at the very bottom, one of the last reactions is to react. This is an azide. If you, I think we covered that reaction in organic 1. If you reduce the azide, you can get the primary amine, and you can remove like nitrogen gas. The very last reaction is then reacting that with acetic anhydride to put the acetyl group and make the acetamide. Two-step reaction. First hydrogen, and then they react with acetic anhydride, make the acetamide, and that's the end product. And that is Zyvox. That's a pretty potent new antibiotic in the past 5 or 10 years. Lots of good chemistry on that. Thank you. Okay, so there was some miscellaneous stuff there. But I want to get us back to aldehydes, ketones, unless we cover everything.
It's just a simplification of the aldehydes.
Yeah, the yellow sheet is where we ended for test 3. Okay, reactions of aldehydes, ketones. Roman numeral 1 and then Roman numeral 2. Roman numeral 1 is non-reversible reactions. What do we mean here? This is when the nucleophile that's added cannot act as a leaving group. And we've already done reactions like this on the yellow sheet. Where we add a nucleophile. Okay, it didn't have to be minus, but I'm showing it as minus. This adds electrons up. We get this here, right? Nucleophilic addition. Can this reverse? Now, if it could, these would come down and we would kick off nucleophile. You're certainly not going to kick off an H in this class, or a plain R group like a propyl. Can we kick off the nucleophile? Well, Roman numeral 1 says no. This is going to be called non-reversible. Once the nucleophile adds, it cannot be then kicked off. The only thing you can do is supply proton that can come from water or H+. Put the H there, and you have a product, which is an alcohol. And that's like those we did when we had the 4, and I showed you the products. Except for the ketone, where we kicked off the chlorine. Okay. Now see, these are aldehyde ketones. There's no like chlorine here or O-ethyl or anything. These are benign H or alkyl that are not going to leave. For example, here's another example. Methyl adds electrons up. So we get the methyl added. And then the O- just picks up a proton from water or from acid. The original H is still there, right? Just because I don't draw in the H there doesn't mean it's not there. Okay? So those would be non-reversible reactions. Nucleophile adding, and it can't then turn around and leave. Question, Jordan?
I noticed when you have tiny nucleophiles, I guess you're doing a Grignard when you're doing magnesium iodine. Is there a reason why you don't do magnesium bromide, or are they just identical?
You mean methyl magnesium bromide?
Whenever you do like a tiny nucleophile, like ethyl or methyl, I notice you always do magnesium iodine. Or is that just coincidence?
No, it's because methyl iodide is a liquid.
Oh, okay.
Methyl bromide's a gas.
Oh.
And so methyl bromide is rarely used. And so it's just a practical thing that I'm aware of, and that's why I just gravitate towards. And ethyl bromide is probably a gas. So your very small ones, typically you'd always use the iodide because it's a liquid. So, there's 1,000,001 things like that I just never tell you because we just don't have all that time to point out the nice uniqueness and the intricacies. It really just comes from just the more experience you have with organic chemistry, you pick up on those things. Okay, there you go. Roman numeral 2, which is the rest of the handout, is reversible reactions. This is where the nucleophile can add. You get to this point. But what's possible is if we're to go backwards. That is, the electrons can come back down and kick the nucleophile back off. So this, you can go both ways. Now, that doesn't mean you can't continue on and maybe from here put an H on and get to this point. This is possible. But we'll also see that from here, we can actually lose the OH, which is originally that oxygen which we can lose is originally the oxygen of the carbonyl. So that oxygen we can ultimately lose in the chemistry we're going to see. And we can actually make double bond to our nucleophile. Okay, what type of nucleophiles are these going to be? Well, it's not going to be an H, like a hydride, because those can't turn around and leave. It's not going to be a plain alkyl group or phenyl, like a Grignard, because those can't turn around and leave. Usually these nucleophiles here are going to be heteroatoms, like nitrogens or oxygens. They can act as a nucleophile, but then the nitrogen can turn around and leave. Okay? So these are classified as reversible reactions. Okay. Now we're under Roman numeral 2A. So it's called a simple addition. But we got to keep in mind that it's reversible. Now since it's reversible here, we will talk about equilibrium and how to drive it to this point. Okay? Where we do non-reversible reactions, we don't have to talk about equilibrium because they can't go back.
The equilibrium, like, is there ever like I don't know if it's the same in Jane Camelot. I've always thought they were kind of equal, but like, is there like, if you put like, is there a best way to drive something to the right? Like putting like excess reaction is better than trying to remove some thing on the right. Like I know in Fischer esterification we did like both add a lot of acid and remove the water, like or like alcohol. Excuse me. Like
let's wait till we get to the example. Usually we'll
case by case.
we'll drive it by removing water.
Okay.
It'll be very similar. Let's wait till we get there and we can hone in on your question.
All right.
Okay. First, let's react an aldehyde or ketone. Everything we're doing is aldehyde ketone. I may show ketone, but it applies to aldehyde. They're not acid derivatives. We're doing aldehyde ketone chemistry here. Your reversible reactions are typically always going to apply just to aldehydes, ketones. Okay, we can react an aldehyde or ketone with just water. And if you do, you get what's called a hydrate. Added water. Also known as a gemdiol, with geminal meaning twins. The OHs are on the same carbon. Okay? Guess what? That's a reversible reaction. Because we're under Roman numeral 2, right? Okay? So it's reversible. But this is an end product. Well, kind of. The reaction can be catalyzed by acid or base. Which one do you want to do? Base. Okay, if it's base, that means we have also hydroxide that we're going to add in. Okay? What's the first step you want to do here? Do you want to protonate carbonyl?
No.
Because that's going to still apply. If you're under acidic conditions, the first thing you'll always do, protonate carbonyl. Where about a third of you on the quiz did not do that. Alright? Are we under acidic conditions? No. What are we going to do first?
Water attacks.
Why would water attack when you got a stronger nucleophile? Use the stronger nucleophile. Hydroxide attacks. What does that give? It's going to give O minus. Boom. Boom, right? That's just nucleophilic addition. Now can this go backwards? Can this come in, form carbonyl, kick off hydroxide?
It could, but it's gonna go backwards.
It could. Anytime you make a pi bond kick off the leaving group, okay, a heteroatom will always leave. This can go backwards. But how do we get the hydrate? What do we need to do? We need to supply an H. What can supply the H? Water supplies the H. What do we get? It gives that plus what? Plus hydroxide. Catalyst reformed. All this is a simple addition followed by putting on a proton. Simple addition, put on a proton. The nucleophile just happened to be an OH. And so at this point we have OH-OH. When you got two OHs, that's called a hydrate. That's the hydrate of the aldehyde or ketone. Also a gem-diol. Now, hydrates are not stable. That is, this equilibrium, this side is favored. Your carbonyl compound in water is favored side. You cannot make a hydrate and then extract it and isolate it and go do an IR. So hydrates can't be isolated. They occasionally appear in mechanisms. Where did we see hydrate at during test 1? If I have I do have it. Easy to find when you got colored paper. Aldehyde carboxylic acid oxidation. What's required for this oxidation other than big 3? Water. Water, and you get the hydrate. Then when the hydrate loses 2 H's, carbonyl OH. Carbonyl OH. Okay? Let me end here, guys. Now, aldehydes, ketones, and water make a hydrate. Now, what do we know about this equilibrium? Which is favored, aldehyde, ketone, or hydrate? Yes, this is favored. This way is very small. That's okay. You may only have one of these out of a million. But that one gets oxidized, then what happens to this equilibrium? It shifts and you make more of this. So eventually all this will be pulled because of this moving on. Okay? Last thing, guys, there is some hydrates that are stable. For example, chloral hydrate is a stable hydrate. On Friday, I want you to tell me why it is. If this is CH3, it's not stable, but with 3 chlorines it is. Also, what is the aldehyde or ketone that this comes from? So go backwards. If you're shown a hydrate, can you show the original aldehyde or ketone? Okay guys, on Friday, please have a look at this handout some. Also the one I'm going to send you by email. Just on Wednesday, we'll get started at the top of the hour.